SwayamPrabha. Digital India. Educated India.
Welcome to lecture number 38 of the Statistical Thermodynamics course, right? So in the last lecture, what we did was that we found out that, for example, internal energy is written as U by RT is equal to T dln Z dr plus T dln Z rotation by dt, so is a V, plus T dln Z vibrational by dt, V plus T ln Z electronic by dt. Okay. The entropy, on the other hand, specific entropy, given as S by R to S R, translational plus S by R rotational plus S by R vibrational plus S by R electronic. Okay, electronic. So this is the specific entropy. Okay. Now for the translational mode, so in this case, translational mode SRTR is written as dln ZTR dt, V plus ln ZTR by n plus 1. Okay, and then of course you have the internal mode, which is given as ln Z internal divided by dt, V plus ln Z internal. Okay, for each of the internal modes, for each of the internal modes. Okay. So separation of energy modes also facilitates the separation of energy modes also facilitate probability calculations okay, associated with stat thermal. Associated with stat thermal. For example, if you want to find out P, let's write it as P. P rotation, vibration, electronic, which means that the probability of being in a specific rotational, vibrational, and electronic energy level, okay, which would mean the number of particles in that rotation, vibration, and electronic configuration divided by the total number of particles, which essentially translates now to G rotation, G vibration, G electronic divided by the corresponding partition functions, C rotation, G vibration, C electronic, and then of course there is an exponential term, okay, which is minus E rotation plus E vibration plus E electronic divided by KT, okay, where we know that the partition functions are like this. The Z internal is equal to Z rotation, Z vibration, Z electronic, and the G internal, which is the degeneracy, is G rotation, G vibration, and G electron. Okay. So this represents what? This represents the probability of a particular probability of being in a particular or a specific rotational, vibrational, and electronic energy level. Okay. Now, if we want to evaluate like this, the probability, say, of being okay, in a specific rotational energy level, being in a specific rotational energy level, regardless of vibrational and electronic energy levels. Okay, we can say that P rho rotational is equal to N rot by N, okay, which is double summation, the sum over all the vibrational levels. This is sum together of all the rotational levels now, right? So G rot, G vibration, G electronic divided by Z rot, Z heap, and Z EL. And then of course everything is still within the summations. So, and this is minus E rot plus E vib plus electronic divided by KT. So you can see that we have summed over all the rotation and over all the electronic energy levels because we are interested in a particular rotational energy level, and we are not really concerned about what are the corresponding vibrational and electronic energy levels. So this is G rot divided by Z rot exponential energy rot by KT. Okay, so of course that's it. Vib is summation over all the vibrational energy levels, KT, and Z electronic. Z electronic is summation over all the electronic energy levels. All electronic energy levels. Okay, summation minus EL KT. Okay, so these are mainly the two for independent energy levels. The Boltzmann distribution may be applied in the same fashion to any single mode as well as to any group of such energy modes. Okay, so as well as to any groups of such energy modes. For independent energy modes are the Boltzmann distribution may be applied okay, in same fashion to any single mode, okay, as well as to any group such energy modes. Okay, so now, this stage is the set that we know now how to calculate the probabilities, how to calculate the properties, because properties always depend on your partition function, actually more specifically on the logarithm, natural logarithm of the partition function. So now we come to the chapter where we say energy mode contributions in classical mechanics. So now the stage is set that we consider the classical contributions from various energy modes to the macroscopic internal energy and heat capacity. Okay. So our eventual goal is to compare the classic and the quantum allocations from each of the translational, rotational, and vibrational modes. Okay, so let us consider classical contributions from various energy modes, okay, to the macroscopic, macroscopic internal energy and say heat capacity. Okay, okay. So our goal, as we said, is to calculate the allocations from each of the translational, rotational, and vibrational modes. Okay, so if we look at a very classical definition, of a system, each atom of a system. Okay, say from a classical perspective, from classical perspective, okay, each atom, okay, each atom of a molecule, okay, can be recognized and be characterized by three position coordinates. It's like X, Y, Z. Okay, now if a molecule has n atoms, okay, the temporal motion of the entire molecule, okay, requires 3n position coordinates, right? Mostly these are independent of each other, so the position of one atom is not dependent really on the other, right? So 3n position coordinates. So we therefore say that the molecule has 3n degrees of freedom. The molecules has 3n degrees of freedom. Now for a diatomic molecule, okay, diatomic molecule, where there are two, the number of atoms is 2, so there would be like 6 degrees of freedom. 6 degrees of freedom. Okay, so how are these 6 degrees of freedom? So altogether 6 degrees of freedom. We can first do this. Out of these 6 degrees of freedom, 3 degrees of freedom, X, Y, Z, is concerned with the first 3 degrees of freedom are used to describe translation of the molecules center of mass. Okay, 2 degrees of freedom, 2 DOFs, okay, are needed to describe its rotation These are needed to describe the rotation. Describe rotation about two orthogonal axes, the y comma z, perpendicular to the internuclear axis, the internuclear axis. Okay. And then there is 1 degree of freedom still remaining, okay, which is used to describe vibration along the internuclear axis. Okay. So this can be the 6 degrees of freedom. First 3 XYZ describes a translation of the center of mass. 2 degrees of freedom are required. These 2 degrees of freedom considers rotation about the 2 orthogonal directions from the internuclear. This is the internuclear axis. The 2 orthogonal directions represents the 2 degrees of freedom for the rotation. And then lastly, vibration can happen along this internuclear axis. So therefore, it has got 1 degree of freedom. Okay? So this has got a very robust link now, consistent with this description. Okay, we recall that in quantum mechanics, the translational mode leads to three quantum numbers. Okay, 3 quantum numbers. The rotational mode leads to 2 quantum numbers. And vibrational mode leads to 1 quantum number. Right? So leads to 1 quantum number. So we can see each degree of freedom. So we can almost say each degree of freedom, okay, is represented or can be associated with a quantum number. Okay? So there is a very robust link between classical and quantum mechanics. So there exists a robust link between classical and quantum mechanics. Okay, so there exists this very nice, association, I should say, between the two. Next, let us look at something called the phase integral. Okay, now to assess the contribution from each classical energy mode to the internal energy U or specific heat Cp, we must develop classical representation of a partition function. Okay, so in pursuit of this goal, we introduced this concept of phase space, which provides a necessary link between quantum and classical mechanics. Okay, so this end we will. So first, let us write down the obvious. The phase space does 2 things. It links quantum and classical mechanics. And used to assess the contribution okay, from each classic mode, okay, to internal energy, U or specific heat, CV. Okay, so let us recall the one-dimensional harmonic oscillator. 1D harmonic oscillator. Okay, the harmonic oscillator. Okay, the Hamiltonian defining the total energy of a conservative system. The Hamiltonian, which describes the total energy of a conservative system. So if we write that E comma E square to mu plus half A naught square. This is the Hamiltonian for the total energy of a conservative system. Okay, P and R are momentum and position respectively. Okay, so this equation that you see over here, okay, is an important result from classical mechanics. Mandates that each degree of freedom mandates a position and momentum coordinate, right? In fact, the central importance of momentum and position in classical mechanics is manifested by the phase space diagram. Okay, so phase space diagram will be something like this. So you have the momentum and the position, right? And you can represent, okay, a different value of the energy. Okay? If you look at it like this is P, this is R, and then you have okay, so each is like dr, and then there is a dp. Say if you look at this, okay, so each dpdr cell represents different continuous value of energy. Okay, continuous value of energy. So each cell can be representing a single classic value of continuous energy, right? Classic value of continuous energy. Therefore, we must assert that the number of quantum states within a cell in a single cell in the phase space must be the classical analog to degeneracy. Okay, so number of quantum states, okay, within a single cell in phase space must be classical analog to degeneracy. Okay, so the correspondence principle indicates that the classical solutions must be replicated by quantum mechanics in the limit of continuous energies. Okay, so in the limit in the limit of continuous energies, continuous energies, that is delta E plus the kT. Okay. The classical solutions must be replicated by the quantum mechanics. Classical solutions are replicated by quantum mechanics. Right? Replicated by quantum mechanics. For single UF, degree of freedom, the classical version of the partition function. So the classical version of partition function becomes, so one is Z summation J by kT. This is almost equal to integral E by kT dg. Okay? Or in other words, this is equal to exponential minus h p comma r by kT. Okay, so dg represents the degeneracy or 1 DOF in the energy range. The energy range. Okay, so E plus dE, because the classical energy can be always portrayed with the phase space, we assume that the quantum counterpart to the differential degeneracy of one momentum coordinate to the other can be explained now, can be expressed now as C dP dr, where C is a constant. Is a constant to ensure classical quantum results agree classical limit. Okay, so substituting this, we can have dz is equal to C, and there are two integrals, EH p comma r by kT dr. Okay, so this will be the partition function in that limit. Okay, for the classical counterpart to the differential degeneracy. Okay, so this is what it is, where the integration is carried out over all phase space, integrated over all phase space. Okay, and this can be also written as phi. And this is called the phase integral. In the next class, we will see that how this result can be subsequently used. Okay, how this can be used to establish contributions from the different modes. So we will see in the next class. We will stop here and take it up in the next lecture.